This is the screencast for section 5.1, example 3. We're going to find the volume of a sphere using this whole chopping it up into kind of rectangular bits, except a rectangle only has 2 dimensions, a sphere is 3-dimensional. So if we take a circle and cut that circle into our rectangular pieces, and then take those rectangular pieces and spin them about the x-axis, we will get what looks like several cylinders stacked on top of each other, which will be our estimate for a sphere. So we're going to take each of those rectangles and spin them, or find the volume of each one of those cylinders. So I'm going to look at the volume of a cylinder for each one of these cylinders and estimate the volume of the sphere of radius 4. Okay, well, the volume of a sphere is pi r squared times h. I'm going to call the radius of this sphere the y value, and then the height of the sphere is going to be kind of the thickness, or really in this case delta x. So the sphere, if I cut it into 8 different cylinders, is going to have 8 different parts, but really it's going to be symmetrical. So I'm going to take 2 times each one of those 4 cylinders on the right side, and that'll get me the right half and the left half of that sphere. So I have 4 cylinders, each pi r squared times height. Well, the height of each of them, or the thickness, is going to be 1 because it's got a radius of 4, and I'm cutting half the sphere into 4 cylinders. So the delta x in this case, the change in x or the thickness, is going to be 1. Now the question is, do we use the left of each of these cylinders, the right, or the middle? Well, as you saw from examples 1 and 2, sometimes the left and the right tend to be way overestimate or way underestimate. So I'm going to use the middle in this case. The middle is a good safe one. If the directions don't tell you which one to use, go ahead and use the middle. So I'm going to plug each one of those x values, 1 half, 3 halves, 5 halves, and 7 halves, into the function to find out the actual radius of each one of these cylinders, or I guess it would be height of the y coordinate. And then, so when I plug that in, I have to plug that into the square root of 16 minus x squared, this equation for the semicircle up here. Now I can tell my calculator to help me with that too. So I put in y1, the square root of 16 minus x squared, and then I did 2 pi, which I factored out the pi, and then times y1 of 0.5 plus y1 of 1.5 plus y1 of 2.5, and all of those of course squared because it's radius squared. And then my final answer, after doing this, would be 270.18 units cubed, which is my estimate using this cylindrical method. But my real value, if I just take 4/3 pi r cubed and plug in 4 for cubed, is 268. So this was a slight overestimate. Then I'll try problem number 13. I'm going to show you an opportunity we have to let our calculator help us a ton. First, on the left side here, I'm going to show the work to show you why this is okay, but then I'll show you all you need to do to produce the answer. Alright, so number 13, continuation of example 3. So we're going to use the slicing technique of example 3, so those cylinders, to find MRAM sums that approximate the volume of a sphere of radius 5 this time. So that means I'm using the equation the square root of 25 minus x squared. And then I'm going to use n equals 10, 20, 40, 80, and 160. Okay, so there's no way I'm going to want to do all of those cylinders by calculating those by hand. No way. So as the problem suggests, we can use the area program on our calculators, the MRAM. So first, the volume of this is going to be pi r squared times height plus pi r squared times height plus pi r squared times height for however many cylinders you want to break this up into, whether it's 10, 20, 40, 80, or 160, it doesn't matter. Which means I'm going to take pi, and instead of r sub 1 squared, I'm going to plug in that r sub 1 into f and square that to find out the height of each of the radiuses according to the curve around the outside of the sphere there. So here I actually did plug that in, so it's pi and then square root 25 minus r sub 1 squared, r sub 2 squared, etc., r sub n squared, of course times the height for each one of those. So far nothing new, I'm just doing this the long way. Now of course a square root squared is just a 25 minus r sub 1, 25 minus r sub 2, etc. Now I factor out pi. Now here's where it becomes a little bit different. I'm going to call this new equation times h g. So instead of f being the square root of 25 minus x, as we had previously defined it, now g is going to be what happens after you square it. So 25 minus r sub 1, 25 minus r sub 2, 25 minus r sub n. So then after I've squared it, I've got this g of r sub 1, g of r sub 2, g of r sub 3, etc., all the way to g of r sub n, which doesn't have to use the square anymore because the square canceled out the square root from the equation in the function that created the sphere. That is the definition of RAM. That is height times width. The y-coordinate times the width on the x-axis. G of r sub 1, the height, times h, the change in x. Then a new rectangle, g of r sub 2, times the height. Then a new rectangle, g of r sub 3, times the height. So we have pi times MRAM, and that will get us all of our answers, which is really, really nice. So in this case, I want to keep in mind that the actual volume of my sphere is 4/3 pi and then times 5 cubed, so 523.6-ish cubic units. I'm going to keep that in mind when I do my estimates to make sure that they're, at least estimates, they're close. So I calculated my RAM up here, MRAM, with my calculator, and I found that the MRAM was 167.5, so all I did was take pi times 167.5. and I get my estimate, which is pretty close. Same thing, I did it with my calculator, MRAM with 20 cylinders, and that was 166.875, multiplied, got my new estimate, etc. I can do that for 40 cylinders, 80 cylinders, and there's my 160 cylinders. So basically, all I had to do was think ahead. What does MRAM mean? Well, it means the height times the width. Well, if I'm squaring it, and I have a function with a square root, that's the one I want to use for RAM. I couldn't have used RAM with the square root of 25 minus x squared because I would have had to square each one of those, and I can't factor out the square to just use RAM. I would have had to individually square each first and get rid of the square root. That's the function that I can use RAM with. 25 minus x squared, not the square root of.